Learn like a pro.
Hey everyone, and welcome. Today, we're diving deep into the energetic world of chemical bonds. We're going to figure out why some things, like a campfire, get super hot, while other things, like a chemical ice pack, get crazy cold. Let's get right into it. So, think about it. You're sitting by a campfire, and it's radiating all this wonderful warmth. But then, you crack one of those instant ice packs for an injury, and it gets unbelievably cold, right to the touch. They're both just chemical reactions happening. So what gives? What is the fundamental difference here? Well, the secret to this whole hot and cold mystery, it actually lies in this fundamental two-step process. It's kind of like a dance that every single chemical reaction performs. And it's all about the breaking and making of chemical bonds. Okay, so here is that rhythm. Step one, you've got to break the bonds that are holding the original molecules, the reactants, together. And listen, this part always, and I mean always, requires you to put energy in. Then comes step two. New bonds form to create the products, and this process always releases energy out. Every single reaction is just a balance of these two steps. You know, a really great way to picture this is with Legos. Imagine you've got two bricks that are really stuck together. It takes a little effort, right? A little bit of energy to pry them apart. That's your bond breaking, energy in. But snapping two new bricks together, that's easy. It gives you that satisfying click. That's bond making, energy out. So if energy is constantly going in and constantly coming out, how do we know what the final result's going to be? Well, chemists basically keep score. They have a sort of chemical ledger to track whether a reaction ends up with a net loss of energy or a net gain. First up, we've got an exothermic reaction. This is our campfire. In this case, the energy that gets released when all those new bonds are formed is way greater than the energy you had to put in to break the old ones. So the reaction has a net release of energy, which escapes as heat and light, warming up everything around it. And on the flip side, we've got our instant ice pack. This is a perfect example of an endothermic reaction. Here, it takes more energy to break the starting bonds than you ever get back from forming the new ones. So to make up for that energy shortfall, the reaction literally has to pull heat energy in from its surroundings, which is why it feels so cold. This slide just sums it all up perfectly. For exothermic, think exit. Energy exits the system. The temperature goes up, and its special energy symbol delta H is negative. For endothermic, think enter. Energy enters the system. The temperature drops, and its delta H is positive. Seriously, that one little positive or negative sign tells you the entire story of the energy flow. But hold on, there's a little catch. Reactions don't just happen out of nowhere. I mean, even a campfire needs a match to get it started, right? This initial investment of energy has a name. It's called activation energy. It's the bare minimum energy you need to get over the hump and kick off that first bond-breaking step. And these two diagrams show us exactly how chemists visualize this whole process. See, the simple energy level diagram just shows you the starting and ending points. But the energy profile diagram, now that gives you the full story. It shows that activation energy hump that the reactants have to climb over before they can become products. And you know what's cool? This isn't just some vague concept. We can actually put real numbers to it. By looking at the strength of every single bond involved, we can calculate the exact energy change for a reaction and prove, with math, whether it's exothermic or endothermic. The key value we use to do all this is called bond energy. It's measured in something called kilojoules per mole, and it tells us precisely how much energy it takes to break 1 mole of a very specific bond. And, of course, that's the exact same amount of energy that gets released when that bond is formed. Let's look at some examples. As you can see here, it takes 436 kilojoules to break apart a mole of hydrogen-hydrogen bonds. But look at chlorine-chlorine, it only takes 242. What does that tell us? Well, it tells us that the HH bond is a whole lot stronger and tougher to break than the Cl-Cl bond. All right, let's use these numbers to figure out a real reaction. Hydrogen gas reacting with chlorine gas to make 2 molecules of hydrogen chloride. So the big question is, will this reaction get hot or will it get cold? Let's do the math and find out. Okay, step 1 is our energy investment, what we have to put in. That's the bond breaking. We need to break 1 HH bond, which costs us 436 kilojoules. And we need to break 1 Cl-Cl bond, which costs 242. Add those two together, and our total energy input is a positive 678 kilojoules. Now for the good part, the energy payout. This is our bond making. We're forming 2 brand new HCl bonds. We know from our chart that each one releases 431 kilojoules. So 2 times that gives us a total energy release of 862 kilojoules. And since that energy is being released, we give it a negative sign. And now for the final tally. We just do the simple math. We put in 678, and we got out 862. The net change is negative 184 kilojoules. And because that final delta H is negative, we have our answer. The reaction is definitively exothermic. It releases 184 kilojoules of energy into the world. But look, this isn't just some abstract theory you do in a textbook. This principle of energy balance is happening all around us, and even inside of us, every single second of every day. So let's check out a few real-world examples. I mean, just take the 2 most important processes for all life on Earth. Photosynthesis is this massive, planet-wide endothermic reaction. Plants absorb energy from sunlight to build complex sugar molecules. And then what do? We perform respiration, which is an exothermic reaction where we break down those sugars to release all that stored energy that powers our bodies. It's a perfect cycle. Now, here's a really critical distinction to make. Melting ice makes your drink colder, right? That feels endothermic, and it is. It's absorbing heat. But it is a physical change, not a chemical one. The bonds within the H2O molecules themselves aren't actually breaking. We're just using energy to overcome the weaker forces between the molecules to let them slide around. A true chemical reaction like fire involves a total rearrangement of the atoms themselves. So if you take just one thing away from this whole explainer, please let it be this. That little symbol, delta H, is everything. A positive sign means the reaction has to pull energy in from its surroundings, making them colder. A negative sign means the reaction pushes energy out, making the surroundings hotter. It is the entire story of energy flow, captured in a single symbol. And all that leaves us with one final, fascinating question to think about. We've seen that even energy-releasing exothermic reactions need that little spark, right? That activation energy to get them going. Our bodies are constantly running millions of chemical reactions just to keep us alive. So, where does all that startup energy come from? What's the spark inside of us? Something to ponder. Thanks for watching.